This is the cover of a book on computer experiments in math, published in 2004. On page 56, the authors posed the following question. They asked whether this infinite series converges. They wrote that this is an open problem, meaning they couldn't solve it, and the folks they asked couldn't solve it either. I'm pleased to report progress on this question. A year later, the problem was solved. In fact, I solved it. I first saw the problem mentioned on the Art of Problem Solving forum. I wrote a solution there, and later wrote a paper on the problem. I'd like to share the solution with you. The solution involves the number pi. In particular, we'll need to know how closely pi can be approximated by fractions. We'll use a result about pi that may be new to you. Are you ready? Let's go. Here is the infinite series again. First, a clarification. When we write sine n, we mean n radians, not n degrees. In serious math, angles are in radians by default. If we wanted degrees, then we'd include the degree symbol. We're trying to determine whether the infinite series converges or diverges. Converges means that the partial sums head to a finite limit. Diverges just means doesn't converge. In this case, diverges means that the partial sums head to infinity. Before going further, take a guess. Do you think that the series converges or diverges? Let's find out if you're right. There are standard tests for infinite series. We have an infinite series of positive numbers. We're trying to figure out whether the series converges or diverges. As an example of one of the standard tests, consider the root test. In the root test, we look at the nth root of the nth term. We'll look at the limit of those roots. To be precise, let R be the lim sup of those roots. Lim sup stands for limit superior. If you haven't seen lim sup before, think of it as the upper limit. The value of R will help us determine whether the series converges or not. If R is less than 1, then the series will converge. Basically, it'll be bounded by a geometric series. On the other hand, if R is bigger than 1, then the series will diverge. In this case, the series will head to infinity. Finally, R might equal 1. In that case, the root test is inconclusive. The series could converge or diverge. What do you think the root test will say for our series involving sine? Let's find out. Here is our original series, and here is the nth term. In the root test, we look at the limit of the nth root of the nth term, like this. In our case, the nth root of the nth term simplifies nicely because the exponent of n goes away. Here's what we get. What can we say about the nth root of n itself? It approaches 1 as n goes to infinity, so we can remove it from the limit. The value of sine n oscillates between -1 and 1, so its upper limit is 1. Let's plug that in. We find the entire upper limit to be 1. What does that mean? That means the root test is inconclusive. The root test won't help us. The same is true of the other standard tests. So we're on our own. Let's take a fresh look at our infinite series. Looking at the series again, the denominator is pretty simple. It's just n. On the other hand, the numerator is complicated. It's a sine expression raised to the nth power. Let's look at a couple of graphs associated with it. We'll start with the sine expressions without the exponent. Okay. Here's a graph of 2/3 plus 1/3 sine n. It's a nice periodic sine wave. The average value is 2/3. The values oscillate from a low of 1/3 to a high of 1. Next, let's raise this expression to the power n. Here is a graph of the numerator of our infinite series. The graph is no longer periodic because the exponent n is growing. Still, the graph oscillates. The low value approaches 0 without ever quite hitting 0. For example, if we have something like 1/2 raised to the 30th power, then the value will be less than 1/1 billion. barely distinguishable from 0. Indeed, for most values of n, the value of the expression is really near 0. That could be an important observation later. On the other hand, the high value is 1, provided we allow n to be any real number, not just a whole number. Can we use the upper bound of 1 to solve the problem? Let's find out. Here is our infinite series again. We know that the numerator is at most 1. We get a new infinite series. Have you seen that series before? Let's expand it out. 1 plus a half plus a third, and so on. Do you remember the name of that series? It's the harmonic series. And what do you know about the harmonic series? It diverges to infinity. That means the partial sums become as large as desired, eventually passing 1,000, 1,000,000, and so on. We have shown that our original sum is at most infinity. Does that tell us whether the original sum converges or diverges? No. The comparison is inconclusive. Our original sum could converge to a finite number or diverge to infinity. We need to do more work. In this attempt, we bounded the numerator by 1. If we had even a slightly better bound on the numerator, then we could solve the problem. Let's try again. For example, suppose the numerator were bounded by 1 over n for every positive whole number n. That would be great. We could then bound the original sum as follows. And we can simplify. Does this new sum look familiar? Let's expand it out. Now does it look even more familiar? It's the sum of the inverse squares. Do you remember what the inverse squares add up to? They add up to pi squared over 6, around 1.64. That's a spectacular result due to Euler from 1734. In particular, the series converges. We didn't need the exact value. For example, it's pretty easy to show that the sum of the inverse squares is less than 2. Okay, assuming that our hypothesis is correct, we've bounded our original series by a larger convergent series. What does that say about our original series? It would converge too. This approach would show that the original series converges, except there's a big if at the start of our argument. And so the question becomes, is our hypothesis true? What do you think? Is this inequality true for every positive whole number? Alas, the answer is no. There are many counterexamples. 2, 3, 7, 8, 9, 14, and the counterexamples seem to keep going. The attempted solution breaks down. But not all is lost. We can split the positive whole numbers into two camps, those that satisfy the inequality and those that don't. We can then try to handle the two cases separately. Let's try that. We'll check if the number n satisfies the given inequality. If it does, we'll call n tame. Otherwise, we'll call n wild. The tame numbers are good, while the wild numbers are bad. We'll try to deal with the two cases separately. Here is our original infinite series. We'll split it into two series. The first series will sum over the tame numbers. The second series will sum over the wild numbers. Because all the terms are positive, it's fine to rearrange the series in this way. Our original question turns into two sub-questions. First, does the tame series converge? Second, does the wild series converge? If both series converge, then the original sum converges. Otherwise, the original sum diverges. So we've broken the original problem into two separate questions. Let's try the tame series first. Here is the tame series. We're just summing over the tame numbers. Do you think the tame series converges or diverges? Let's see. We can use the definition of tame to bound the numerator. We've bounded the numerator by 1 over n. Let's simplify the resulting expression. We have a sum of inverse squares, except we're just summing over the tame numbers. We can bound this series by summing over all positive whole numbers. Does this sum look familiar? Yes, it's the famous sum of inverse squares, and we know what that is. It's pi squared over 6. We've bounded the Tame series by a larger convergent series. What does that mean about the Tame series? It converges too. Yay! We crafted the definition of Tame to make sure the Tame series converges. We no longer have to worry about the Tame numbers. The rest of our work will focus on the wild numbers. Here is the wild series. We're summing over the wild numbers. For wild numbers, we have little control over the numerator. All we know is that the numerator is at most 1. Let's use that. We have to add up the reciprocals of the wild numbers. The sum depends on how rare the wild numbers are. If there are lots of wild numbers, then this sum will diverge. Otherwise, the sum will converge. So, how rare are the wild numbers? Let's gather some data. Here is a chart showing how frequent the wild numbers are. In the range 1 to 10, half the numbers are wild. But in the final range here, from 1 to 1,000,000, less than 1% of the numbers are wild. It looks like the wild numbers are becoming rarer and rarer. We need a plan to actually prove that claim. Here we'll outline our plan for controlling the wild numbers. First, we'll show that the sine of a wild number is near 1. That will follow from the definition of wild. Second, we'll identify where the wild numbers are near. That will follow from properties of the sine function. The third step is the hardest. We'll show that the gaps between wild numbers become large. Fourth, we'll show that the wild numbers are indeed rare. Namely, we'll show that the wild numbers grow faster than a linear function. Finally, we'll show that the wild series converges. Okay, that's our 5-step plan. Are you ready to begin? Let's go. We'll start with step 1. We'll show that the sine of a wild number is near 1. Remember, this was the definition of a wild number. It's an inequality on the numerator of our infinite series. Let's solve this inequality for sine. Namely, let's take the nth root of both sides. We get this inequality. Now we can solve for sine n. Namely, multiply by 3 and subtract 2. We get a nice inequality, but we'd like to estimate the final expression, so let's rewrite it. We have rewritten the base n as e to the log n. Okay, we've solved for sine n, but what can we say about that final expression? Is it near 0, near 1, or something else? Let's find out. Okay, so here's what we just showed. Let's estimate that final expression. We'll use the fact that e to the x is always at least 1 plus x. We get the expression here. Let's simplify a bit. This expression is nice, but it would be nicer if n appeared just once, not twice, so we'll replace the log. We can do that because log grows slower than square root. Okay, we have a nice bound. Putting it all together, we get, if n is a wild number, then sine n is bigger than 1 minus 3 over the square root of n. In other words, sine n will be near 1. We've completed step 1. We know sine n is near 1. In step 2, we'll identify where the wild numbers are. For that, we'll need to remember how the graph of sine looks. Here's the graph of sine. Its maximum value is 1. And where does it attain that maximum? One place is at pi over 2, which is 90 degrees. There are other places, since sine is periodic. For example, we can add 2 pi to pi over 2, or we can add 4 pi, 6 pi, and so on. In other words, sine n is 1 if and only if n is pi over 2 plus a multiple of 2 pi. We get an approximate version of that equivalence too. sine n is approximately 1 if and only if n is approximately pi over 2 plus a multiple of 2 pi. That's an informal statement since we haven't specified what we mean by approximately. Next, we'll develop a more quantitative statement in the context of Wald numbers. Suppose that n is a Wald number. In step 1, we showed that sine n is this close to 1. We want to say something about n itself. We can write n as pi over 2 plus some number epsilon plus a multiple of 2 pi, where epsilon is between minus pi and pi. We can do that because we can always choose the multiple of 2 pi to be near n. At the start, we only know that epsilon is between minus pi and pi. Our goal is to show that epsilon is much smaller than that. Let's express sine n in terms of epsilon. Sine n is sine of pi over 2 plus epsilon because we can ignore the multiple of 2 pi. Do you remember a trig identity to simplify sine of pi over 2 plus epsilon? It's cosine of epsilon. Next, we need to approximate the cosine of epsilon. It's at most 1 minus epsilon squared over 5. That's related to the fact that when epsilon is small, cosine of epsilon is approximately 1 minus epsilon squared over 2. The factor of 5 makes the inequality true for all epsilon between minus pi and pi. Let's look at what we have here. On the one hand, sine n is bigger than 1 minus 3 over the square root of n. On the other hand, sine n is at most 1 minus epsilon squared over 5. That means epsilon squared over 5 is less than 3 over the square root of n, which simplifies as follows. Epsilon squared is less than 15 over square root of n. Let's replace the 15 with 16 to get a perfect square. So epsilon is small, as we wanted. In absolute value, it's at most 4 over the 4th root of n. Let's summarize what we just showed. We just showed that if n is a Wald number, then it's near pi over 2 plus a multiple of 2 pi. Namely, it's within 4 over the 4th root of n of such a number. That means we finished step 2. Next, we'll tackle step 3. We'll show that the gaps between Wald numbers are large. By large, think of some root of n. Suppose we have 2 Wald numbers. We'll call the smaller one n. We'll call the bigger one n plus gap. For now, we'll assume that n is bigger than 5,000. When analyzing convergence, we can ignore the first few terms. We'll use the result of the previous step. Recall that n is near pi over 2 plus a multiple of 2 pi. The same is true for n plus gap. By subtracting, we see the gap itself is near a multiple of 2 pi. Let's keep going. What does it mean to be a multiple of 2 pi? It means it's of the form q times pi, where q is some even number. So gap is quite close to q times pi. Let's solve this equation for pi. We see that pi is near the ratio of gap over q. We know that pi can't be exactly equal to gap over q because pi is irrational. Now, how close can pi get to being a rational number? There are known results along those lines, so let's go on a quick aside to talk about such results. We'll use a theorem due to this guy, Mahler. Not the composer Gustav Mahler, but the mathematician Kurt Mahler. Mahler was born in Germany. Around 1936, he fled Nazi Germany to England, where he did the work we're about to describe. In 1953, he wrote the following paper. As the abstract says, Mahler's paper is about the distance of pi from a given rational number. Specifically, he proved the following theorem, as beautiful as the other Mahler's symphonies. If p and q are two integers such that q is bigger than 1, then pi can't be too close to the rational number p over q. Namely, the difference exceeds 1 over q to the 20th. Note that as a corollary, this result shows that pi is irrational. Actually, in Mahler's paper, he proved a slightly weaker version, where the exponent was 42, not 20. The version listed here was proved in 1982 by Greg Chudnovsky. Since then, even better bounds have been shown. It's an open problem to find the best possible exponent when q is sufficiently large. That problem is called the irrationality measure of pi. For our convergence question, any exponent will do, so we'll use the version listed here. Okay, let's go back to analyzing the gaps between wild numbers. Recall we showed that pi is quite close to gap over q. On the other hand, Mahler showed that pi can't be too close to gap over q. If you put those two inequalities together, we get the following inequality, and we can solve that inequality for q. We see that q is at least on the order of n to the power 1 over 76. And since gap is quite near pi q, we get the following inequality. Gap is bigger than n to the 0.01. We'll even throw in a factor of 1/2 so that we can remove the assumption that n is bigger than 5,000. We've completed the hard step. We've shown that the gaps between the wild numbers are large. Yay! The remaining steps are simpler. We'll use the gap result to show that the wild numbers are rare. To do so, let's give a name to the sequence of wild numbers. We'll name the wild numbers w of 1, w of 2, and so on. The first wild number is 2, the second is 3, and so on. To show that the wild numbers are rare, we'll show that the kth wild number is pretty large. In particular, we'll show that the kth wild number is at least on the order of k to the power 1.01. Because 1.01 exceeds 1, that means the wild numbers grow superlinearly. Let's see how to prove this claim. We'll look at two consecutive wild numbers. We already showed that the gap between them is large, so let's use that fact. Now, the k-1th wild number is at least k, so we can simplify this inequality. Stare at this inequality. We see that w of k is bigger than w of k-1 plus something. That's a recurrence. Similarly, w of k-1 is bigger than w of k-2 plus something. If we completely unwind the recurrence, we get the following sum. It's a sum of powers from 1 to k. And we can estimate that sum in many ways. For example, by approximating the sum with an integral. If we do that, we get the following estimate. And we can simplify. We've shown the superlinear bound that we desired. Great! We've shown that the wild numbers grow rapidly, and in particular, that means they're rare. We've completed step 4 of our plan. Finally, we can show that the wild series converges. Here is the wild series again. It's our original series, except that we're only summing over the wild numbers. We can bound the numerator by 1, and we can use the W sequence to rewrite this series. Remember, we know that the kth wild number is pretty big. We have this series with an exponent of 1.01. Do you remember whether this series converges or diverges? It converges, precisely because the exponent is bigger than 1. If you're curious, the sum of this series is about 300. More precisely, it's about 301.7. All we need is that the series converges. Okay, we've bounded the wild series by a larger convergent series. What does that mean about the wild series? It converges too. we've completed our 5-step plan to control the wild numbers. Super! We can now go back to our original series. Here is our original series. We split it into 2 parts. Early on, we showed that the Tame series converges. We just showed that the wild series converges. And so, the entire series converges. Hooray! In retrospect, splitting this series into 2 parts was the key idea of the solution. The Tame terms are tiny, and so their sum is small. On the other hand, the wild terms are rare, and so their sum is also small. As mentioned near the beginning of the video, I first posted this solution on the Art of Problem Solving forum in 2005. Much later in 2020, I finally wrote a paper with this solution. I've included a link to the paper and more in the video description. Thanks for watching.